Okay, so what we're going over today, guys, is we're going to go over conservation of mechanical energy. Basically, the last big thing that we're going to cover in physics. Okay, we have like a couple of little small things, a little review of thermodynamics and something on efficiency this week, and that's it. Okay, the law of conservation of mechanical energy we've talked about already. It's the first law of thermodynamics. Energy can't be created nor destroyed. Okay, so what we're looking at here are situations where the mechanical energy of an object or a system is not changing. All right, so if the energy is not changing, what is not being done in any of these questions? Work, exactly. All right, that is how you can differentiate between a law of conservation of energy problem and a work energy problem on a test. All right, we kind of talked about how when you're looking at a work energy problem, you're usually going to be given things like force, or it might outright say this much work was done, or whatever. Okay, there'll be those kind of cues in the question. Energy is changing, things like that. These kind of questions, energy is not changing. You'll never see the word work in a question like this. You'll never be given force in a question like this. All right, so they are quite a bit different, all right, than a work energy theorem question. Everyone with me there? All right, so in a question like this, the system starts out with a certain amount of energy. All right, it may have been put in there by doing work, but once that work has been done, no other energy is going to be put into that system. All right, now the energy that's in there, what kind of things can happen to it? Once you have energy in a system, what can the system do with it? It could do work on something else, but that would mean its energy is going to change. Agreed? All right, so we're going to kind of, that could happen, but we're going to eliminate that as one of the options here. Okay? If you have, let's say, elastic potential energy in a system, can it become something else? Yes. Okay? Within a system, that elastic potential energy could become kinetic energy. It could become gravitational potential energy. It could become sound. It could become heat. It could become anything. All right? But it's always going to be in there. Now, we're going to simplify a little bit, and most of the problems we're going to deal with in this are going to have to do with changing one kind of potential energy into kinetic or vice versa. Okay? Everyone with me so far? So, the bow and arrow example we come back to because it's a great example of not only work energy theorem, but also of conservation of energy. Okay? If a person does what's going on in this picture, okay, they aim their bow and arrow straight up in the air, and they draw it back. Is there potential energy stored in the bow? Can that potential energy become kinetic energy? Yes. Can it become gravitational potential energy? Will it? Yes. Okay? And in the perfect physical world, if you did 100 joules worth of work on the bow, the maximum amount of kinetic energy the arrow could have would be 100 joules. What about the maximum gravitational potential energy? 100 joules. Okay? Is it possible for it to have 50 joules of each? Certainly. Okay, about, well, not quite halfway, but part way to the maximum height of the arrow, it would have about 50 joules of each. Okay, so that's what we're going to be looking at there. So when energy is transferred to an object, it can cause a change in both the kinetic and potential energy simultaneously. Okay, that means at the same time, right? So when you do something, when you do work to something, you could be changing both, and you are if you accelerate something up a hill. All right. So if let's say I've got a ball at the bottom of a hill and I'm rolling it up, and not only am I making it go up the hill, I'm also making it go faster. Okay. I am changing both the kinetic and potential energy of the ball at that time. Okay. All right. Because both of these types of energy, kinetic and potential, okay, can change at the same time, okay, and can be part of the total energy of an object, we call that total energy, okay, mechanical energy. Right? So mechanical energy is always, always the sum of the potential energies and kinetic energies of the object. All right, and obviously it is possible for an object to have both kinetic and potential energies at the same time. Now, do we have formulas that allow us to calculate each? Yeah, okay. We know that potential energy is m times g times h, and we know that kinetic energy is 1/2 mv squared. All right. If I want to find the total mechanical energy of an object, all I do is calculate both kinds and add them together. Is that very hard? Not at all. Okay. All right, so we'll look at this first example here. Okay, example B2.6. So we have this 0.3 kilogram baseball, okay, thrown in a straight line through the air. It has a height of 2.5 meters above the surface of the Earth. Does it have potential energy? Yes, it does. Okay, and it has a speed of 20 meters per second. Does it also have kinetic? Yes. All right, so we want to find the total mechanical energy of the baseball. Well, as we said before, mechanical energy is the sum of an object's kinetic and potential energies. All right, so 1/2 mv squared plus mgh will allow me to calculate the total mechanical energy of the object. So we plug in our numbers here. 1/2 times 0.3 kilograms times 20 meters per second, all squared, okay, plus 0.3 times 9.81 times 2.5 meters. Right? When we do that, okay, we get 60 joules of kinetic, 7.36 joules of potential. Right? And that gives us a total of 67.4 joules worth of energy, of mechanical energy. Okay? Everybody okay with that? Okay? Nothing too terribly complex there? All right. All right. Now, we've talked about the bow and arrow example a whole bunch of times, and that's what this is talking about down here. This paragraph here is just talking about converting one form into another. What I would like you guys to try right now are these little practice problems here that are just like the example we just did. So they're not difficult at all. You're just calculating kinetic and potential and adding them together. All right. And I think I have the answers. Yeah. No, I don't. Yes, I do. All right, so you can check your work as you go. These are the correct answers, okay, to those problems. If you get those, you did it right. All right, so let's have a look at least number 1 here. So we got a seagull flying horizontally at 8 meters per second, carries a climb with a mass of 300 grams. What do I have to do with that? Convert it to kilograms, okay? We can't do any energy calculations with things in grams because a joule is a kilogram meter squared per second squared. If I don't have kilograms for mass, I don't get joules, all right? So if I want to calculate the total mechanical energy when it is 30 meters above the ground, I have to do this. Mechanical energy equals, okay, the kinetic energy plus the potential energy. And so that's going to mean 1/2 mv squared plus m times g times h. So 1/2 times 0.3 kilograms times 8 squared, okay, plus 0.3 times 9.81 times 30. Okay, when I do that, I should get 97.9 joules. Everybody right with that one? Okay. How many people are done number 9? How many people are stuck on 9? No? Okay. Okay, so you got this 55 kilogram high jump athlete leaps into the air, okay, clearing the bar. When they clear the bar, they have 3,000 joules, okay, of mechanical energy and are moving at 8.33 meters per second. They want us to calculate the gravitational potential energy of the athlete. So if we go back to this initial formula, EM equals EK plus EP. How do I get EP? Right, subtract EK from both sides. All right, so EM minus EK will give me the potential energy of the athlete. All right, so not a difficult calculation. I just have to plug in the numbers I was given. 3,000 joules, okay, minus 1/2 times 55 times 8.33 squared. Okay, when I do that, I should get 1,091.8 joules. Okay. Questions on that one? Okay. And is number 10 pretty much the same way, except you had to calculate EK instead of EP? 3 times 10 to the 3? 123,000 joules. Yeah? Okay. Whenever you have scientific notation, guys, if your exponent on the 10 is positive, you move the decimal to the right that many spots. If it's negative, you move the decimal to the left that many spots. That's your new number. In case you didn't know that before. Okay. That's how you convert scientific notation into real numbers. All right. And then for number 10, like we said, if we want to calculate EK, okay, well, EK is going to be the mechanical energy minus the potential energy, okay? Similar to what we did in the last question. So our mechanical energy is, what is that, 1.88 times 10 to the 3? So that's 1880. We'll just write that as 1880. Joules minus, okay, the mass, which is 2 kilograms, times 9.81 times the height, which was 50 meters. That is incidentally why, if you are ever walking through a construction zone, they have those plywood tunnels that you walk through. Okay, it's so that all the stuff that falls off a construction site doesn't hit anyone below, because that's a recipe for a lawsuit. All right, a 2-kilogram hammer hitting you on the head from 50 meters would probably kill you. All right, it would have a lot of kinetic energy by the time it got down there. 899 joules of it, in fact. Okay, and that could do a lot of damage. 900 joules of energy is a lot of work. Okay, everyone following me on those three? Okay, nothing difficult. I know that I'm not trying to belittle your intelligence by having you do something this easy, but it's a stepping stone to what we're going to eventually get to here. All right. Sorry, I'm going to go back one here. So this goes back to the bow and arrow example, but we've kind of talked about this as well. Okay, if I use a force of 100 newtons and I pull back a bow 0.5 meters, how much work have I done? 50 joules, right? Because force 100 times 0.5, the distance is 50 joules. So that's the work done on the bow, and we talked about this already. That means there's how much potential energy in the bow? 50 joules, okay? There's 50 joules of kinetic energy possible for the arrow, okay? And the potential energy of the arrow at its highest point would be 50 joules. 50 joules is the only amount of energy that there can ever be in that system because it's all the work that was done to it. All right, everyone's clear on that part? All right, so the law of conservation of energy here, okay? And again, we've said this before, okay, back at the beginning of the unit, okay? It states that the total amount of energy in any given situation remains constant. It can be converted to other forms, but it's always going to be that same number. All right, doesn't mean that it's necessarily doing useful work anymore, but it's still there. All right, so the amount of mechanical energy remains constant, and in the absence of outside forces, potential and kinetic energy essentially get converted into each other. All right, so for that hammer that was 50 meters off of the ground, right? If it was dropped and it had 899 joules of kinetic energy the instant it hit the ground, how much potential energy did it have when it was dropped? 899 joules. Okay, and that's what we have to realize about law of conservation of energy problems. Okay, one type will get converted into another. Sorry guys, my voice is going to crack all day here. I'm not going through puberty a second time. I would simply not endure that. Okay, I just got a cold and my voice is cracking like crazy. Okay, so potential energy equals kinetic energy in some of these situations. What if, and I'm saying hypothetically here, somebody threw that hammer instead? Threw it straight down. It doesn't just have potential energy then at the beginning, it also has some kinetic energy. All right? Does that mean it would have more mechanical energy at the bottom? Yeah. Okay? It would have the same amount it had at the top, but to calculate how much it had at the top, I'd have to add both that 899 joules of potential plus whatever amount of kinetic it was given through the throwing action. Everyone follow there? Okay? But in the end, it would still have whatever those two added up to as kinetic energy the instant it hits the ground. Yes, we're doing this in the perfect physical world where there's no air resistance. And so things would continue to accelerate indefinitely. But you're right. In the real world, things do reach a terminal velocity at which they cannot fall any faster. Okay, so we're looking at an example problem here of a 1.5 kilogram rock that's dropped over the edge of a cliff. If it's dropped, does it have any initial kinetic energy? No. Okay, different from being thrown. Okay, so it's 30 meters above the surface of the lake. We want to find the speed of the rock just before it strikes the surface of the lake. Okay, or the instant it strikes the surface of the lake. So at the beginning of this question, we have some mechanical energy. Agreed? All right, there's no work being done. So the amount of energy initially has to equal the amount of energy finally, or at the end. Agreed? If there's nothing there to change the energy, there's no air resistance, there's no work being added, then the initial energy and the final energy are equal. Everyone's okay with that? Yes, because that's the law of conservation of energy, right? It can't be created, it can't be destroyed. So initially, if it was dropped, it has potential energy, m times g times h. Okay? Now, could I say that this initial energy is, and be more accurate, say it's mechanical energy? Yes. Okay? And that's what we're saying here. Okay? The initial mechanical energy equals the final mechanical energy. We're saying that here as well. EI and EF stand for mechanical energy. So really, I could write this and just go I, and then do this on the other side. Okay? Am I saying the same thing? Yes. Now, because it's dropped, initially it doesn't have any of this. Agreed? Okay, because no one's imparting any velocity to it. When it's just hitting the lake, what's its height? 0. So it doesn't have any of this. So is the initial potential energy equal to the final kinetic energy? Yes, because the initial mechanical is equal to the final mechanical. Right? The reason I don't like the way that the book does it this way is people think this applies for every situation, that potential is always equal to kinetic, and it isn't. All right? This, what we wrote initially here, that is always true. Okay? The sum of both on each side is always true. All right, I want to solve for the final speed of the rock. How do I get final speed by itself? Right. I divide by half of m and square root. What can happen to those two m's? In this case, they can cancel. I'm not doing anything on the top, right? Okay. The mass of the rock hasn't changed between the top and the bottom, has it? At least doesn't tell us it has. Okay. So we can cancel it. If you don't want to cancel it, you don't have to. Okay. You can leave it in there and plug the mass in on the top and the bottom, and it'll come out to the same answer. Okay. All right. So we've got GHI over 1/2 square rooted will equal VF. So we'll just write that down here. GHI. Okay. Square rooted over 1/2, okay, equals VF. Okay, and that's what they've done here. Or actually, they've written it as 2GH. Is that the same thing? Yeah, it is. It's the same thing. All right. So when we plug in our numbers here, okay, we'll have 9.81 times, how high was this thing? 30 over 1/2. Okay, when we do that, we should get 24.3 meters per second. Okay, which is pretty fast. Okay. Is this making sense, guys? Any really difficult algebra here? Not yet. Okay. What if I gave you a situation where you had all 4 of these? And I asked you to solve for one part of that. Could you still do it? Yeah, you can. Okay? It's just a little bit more algebra. It's nothing really difficult. It's just a little bit more stuff to move around. Right? And that's where we're headed, incidentally. Okay, today is getting to a point where you can solve a law of conservation of energy question that would go something like this. A cannonball is fired from the top of a 100-meter cliff at 45 meters per second. How fast is it going when it hits the cliff on the other side at 50 meters above the ground? Okay, so it would have potential energy on both sides, different amounts, okay, and kinetic energy on both sides, different amounts, but the mechanical energy, beginning and final, is the same. Okay. All right. I want you guys to try these two. They are just like what we just did there. Okay, and I've got the key right there. That's decimal 13 meters, by the way, okay, for part B there. All right, so let's have a look at the first one here. All right, so we got the 10-kilogram water balloon dropped from a height of 12 meters. Calculate the speed of the balloon just before it hits the ground. All right, so is there any work being done between when it's dropped and when it hits the ground? Any energy being added to the balloon? No. The only way that could happen is if somebody could time it perfectly so that as it passed the window they were sticking their head out of, they could slap the balloon and make it go faster. Okay? So that's not happening. All right? So it's got the same amount of energy at the beginning, okay, as it has at the end. EI equals EF. Okay? Since it's being dropped, we know that initially it only has what kind of energy? Potential. All right, so we don't need to bother writing the 1/2 mvi squared. We know it doesn't have any. All right, so we're just going to write the initial potential energy is equal to the final kinetic energy. How do I know it doesn't have any potential energy at the end? Sorry, that should be an F. It's hitting the ground. You can't have any potential energy on the ground, at least not gravitational potential energy. All right, I want to find out the speed of the balloon. Is this just like the example we did? Yeah, it is. Okay, finding VF. All right, so divide both sides by 1/2 of m. Okay, the m's cancel. Take the square root of that, and I've got VF. So VF is going to equal, okay, the square root of 9.81 times 12, okay, over 1/2. Okay, and when we do that, we should get 15.3 meters per second. Now, just so you see what that looks like when you plug it into your calculator. One of two ways to do it. You could do the whole thing, okay, in one step, and have your 9.81, okay, times 12 divided by 0.5, okay, and get 15.3. Or you could go 9.81 times 12 equals, okay, divided by 0.5 equals, and then take the square root of that. Okay, whichever way you feel most confident with is going to give you the same answer. All right, so if you're not real confident in your ability to put the brackets in the right way, don't use the brackets. Do it one piece at a time. All right. All right, and for the second one, you got the kid on the trampoline jumps vertically into the air at an initial speed of 1.6 meters per second. Calculate how high the child will rise. Obviously, this is a very small child, as they only get 13 centimeters off of the trampoline. But, you know, if you're only 3 years old, that's probably pretty exciting. Okay, so what we have again is, okay, our initial energy and our final energy, except this time our initial energy is what kind? Kinetic energy, right? And our final energy, the stuff we're calculating, is potential. So we'll have our 1/2 mvi squared, okay? Since she's on the trampoline, she can't fall any further. She doesn't have any potential energy there. Equals, okay, her final potential energy. How do I know she doesn't have any kinetic energy at her maximum height? How fast is the marker going at its maximum height? 0. Because it's slowing down, slowing down, slowing down, slowing down, coming to a stop before it begins to fall back. Okay? Always at your maximum height, your vertical speed is 0. Okay? All right. So we're solving here now for the final height of the child. So what do I have to do with m and g? Divide, right? All right. So the m's will cancel, and I'm left with 1/2 of VF squared, or VI squared, sorry, over g. So that's going to mean 1/2 times, what was her speed there? So 1.6 squared over 9.81. When we do that, we should get decimal 13 meters. Okay. Questions on that one? Everyone's okay with that? All right. Pulleys. For some reason, when people see a pulley, they somehow misconstrue what a pulley does. Right, Joseph? John. Right, John? Put that away, please. Sorry, Joseph. I don't know why I called him you, but... all right. So when they see this pulley, they somehow think that magically energy can be created within this system. If I want this pulley system to work, which mass has to be above the other? The 2 kilogram mass or the 1 kilogram mass? The 2 kilogram mass. All right? The 2 kilogram mass is the only mass that can drive the system. All right. If I was to reverse this, okay, and have the 1 kilogram mass up here and the 2 kilogram mass down below, is it going to do anything? No. I mean, it might roll until the 1 kilogram mass hit the pulley, right? But that's about it. All right. If I started the 1 kilogram mass up against the pulley, there would be no potential for anything to happen. All right. The 2 kilogram mass is the driving mass here. So, that said, how much potential energy does this system have right now? Good. There isn't any way to calculate it. I didn't tell you how far above the ground the 2 kilogram mass was. I just wanted to see if anyone would shout out a number. Okay, it's good. There's no way to calculate it. All right, let's say that this 2 kilogram mass is 1 meter off the ground. Does it have potential energy now? Okay, so it does. How much? It's 19.62 joules. Okay, how do you know that? Okay, because you go 2 times 9.81, which is 19.62, times 1 meter, 19.62. Okay, it's got 19.62 joules. All right, I just pick numbers I can do in my head. All right, so when we do that, this system has 19.62 joules of potential energy in it. Why doesn't the 1 kilogram mass count here in terms of the mechanical energy of the system? Brett? It's, well, not only is it not moving, but it doesn't have the potential to fall, does it? If I'm holding the 2 kilogram mass right here, the 1 kilogram mass can't fall. It's going to go which way? Up. When I let go of the 2 kilogram mass, the 1 kilogram mass will rise. The 2 kilogram mass will pull it. Everyone follow there? Does that mean that the 2 kilogram mass is doing work on the 1 kilogram mass? It does. All right. So does the energy of the 1 kilogram mass change? It does, because it doesn't have any right now. It will change because not only will it go up, it will also go faster. Now, the 2 kilogram mass is going to fall. Some of its potential energy will be converted to kinetic. Will all of it? No. Okay? That's the place where people start to get this idea that energy can be created. They assume that all of the potential energy of this mass can be converted into kinetic as it falls. But it can't, because some of it is being used to do what? Work on the 1 kilogram mass. All right? Now that's looking at this system individually. Now let's look at the system as a whole. When I let this go, and this begins to fall, the 1 kilogram mass gains potential and kinetic. This gets a little bit of kinetic. But at the end, if I add the kinetic energy of this and the mechanical energy of this, what will it come out to? Right, the first energy I had when I was holding it. That system can never have more than 19.62 joules worth of energy in it, because that's all it had to start with. It will be redistributed among the parts, but it can never have more than that. Okay, do you guys follow me there? Okay, but it's easy to kind of picture that somehow it might, because you see that thing falling, you see the other thing going up, and it's easy to assume that suddenly they both have more. Okay, but they don't. All right, energy is transferred from one to the other within the system, but the system never has more than it started with. Everybody all right with that? Now, you're never going to be asked, at least in Science 10, to calculate individual bits about each box. You will in Physics 20, okay? But not in Science 10. It's just that we need to understand the energy of this system is always going to be whatever it was at the beginning. Doesn't mean that each part will have the same amount of energy. It doesn't have to, okay? As long as the system as a whole has the same at the beginning and the end. Okay, now, we talked about this example here already because I put it out of order. Okay, if you did work on the bow, the only energy the bow could ever have was 50 joules, right? Is that the same thing we're saying here? Yeah, it is. Okay, if I do work in lifting up the 2 kilogram mass, 1 meter, I do 19.6 joules worth of work. That's the only energy the system can ever have. Okay, so what I want you to do then is try 13 and 14. Okay? They're going to make you use kind of what we've done before and a little bit of what we've been talking about here for the last couple of minutes. All right, so in 13, you got the 20-gram dart. What's 20 grams in kilograms? Right, 0.02 kilograms. Okay, is fired from a dart gun with this speed. The total mechanical energy is 0.481. Calculate the gravitational potential energy of the dart. All right, so we've done some like that one. And then number 14 is a pendulum. A pendulum, guys, looks like this, right? It's one of those, it's a ball on the end of a string or a bar, and when you move it up, it swings back and forth. Okay, the clocks used to use them. People hypnotize people with them. Yeah, okay. Right. Okay, so on this first one here, they tell us the total mechanical energy. Yes. Okay, they tell us the total mechanical energy is 0.481 joules. Right? That means that's what the kinetic and the potential energy of the dart add up to. Agreed? Right? So I can say that EM equals, okay, our EP plus EK. I'm being asked to find the gravitational potential energy of the dart, that one. So I need to subtract EK from both sides. So EM minus EK equals EP. So that's going to mean then decimal 481 joules minus 1/2 times the mass of the dart, 0.02, okay, times the speed of the dart squared, 4.1, okay, should give me the potential energy. All right, so when I do that, okay, 0.481 minus 0.5 times 0.02 times 4.1 squared, 0.3129. Okay, everybody all right with that one? Okay. Now, for number 2, with the pendulum. Okay, it's suspended on a 50-centimeter string, which is essentially an extraneous piece of information. You do not need to know that at all. All right. The ball is pulled horizontally up a total vertical distance of 10 centimeters. So, what they're saying is, here's the pendulum at its lowest point. Here's the pendulum at the beginning of this question. It has a height of 0.1 meters. Everyone with me there? All right, so it has what kind of energy? Potential. And it only has potential here because it's not what? Yeah, well, it's not moving yet, right? I'm holding it. I've moved it up 10 centimeters, and I'm just holding it there. So it only has potential energy. When it gets down to here, what kind of energy will it have? Kinetic only, because it can't fall any further. That's as long as the string is. It won't let it go any further than that. All right, so I'm trying to find the speed of the ball at the bottom of its arc. All right, so the mechanical energy equals the potential energy plus the kinetic energy. Do they ever tell me the total mechanical energy? .491 joules. Okay? All right, so the total, it says at the bottom of the arc, the mechanical energy of the ball was 0.491 joules. Okay? What's the speed of the ball at the bottom of the arc? Okay, so at the bottom of the arc, it has this much energy. And it's all what? All kinetic. Do I even need to worry about that part? Or can I just worry about the kinetic energy at the bottom of the arc? Okay? Sorry, I shouldn't scratch out the EM part. I should just scratch out the EP part. Okay? EM equals EP plus EK. But at the bottom of the arc, that's 0. Everyone okay with that? All right. So that means that 0.491 joules of energy equals 1/2 mVF squared. I just want to find VF, so I divide both sides by half of m. Okay, and square root. And I'll have my final velocity. Okay, and that should come out to 1.4 meters per second. Okay, so does this question give you a whole bunch of information you don't need? Yes, it does, including that 10 centimeters. Didn't need that either. Okay, it was completely useless. Now, here's the odd thing. Let's check this out just to make sure that this works. This is the energy it had at the bottom of the swing. Is it also the energy it should have here? Can we double check? told the mass, I'm told the height, and I know 9.81 is gravity, right? Okay. So if I want to calculate the potential energy there, I just do this. 0.5 kilograms times 9.81 times 0.1. Same number? Well, rounded, but it's the same number, right? 0.491 joules. Okay. All right. Questions on that? All right, so in the pendulum here, guys, essentially, it's just what we were talking about. It's one form of energy being converted into another. So potential gets converted into kinetic as it swings back and forth. Okay? In a perfect physical world, a pendulum, once lifted and released, would swing forever. All right? In a perfect physical world, where there was no friction on the pivot point, okay, that thing would swing forever. Because potential and kinetic can keep getting converted back into each other indefinitely. Right? Now, obviously that's not the way it works, okay, in the real world, because there is friction on the pivot point, there's air resistance and all that kind of stuff. The most common example of the law of conservation of energy that we will go over in this unit probably is the roller coaster. Okay? Because it's also a great example of converting one form of energy into another. When you ride on a roller coaster, with the exception of a few of the more modern ones like the Hulk and things like that, okay, you get towed to the top of the highest point on the hill, or on the whole ride. Agreed? Okay. Once you're up there, you have a little bit of kinetic energy because you're rolling, okay, but you have mostly what? Mostly potential. And then the best part of the ride is always right after the first hill, because that's the steepest part where you get, you have your most chance to get lots of speed. Okay, so you go down that first hill, you convert all of that potential energy into kinetic, all right? And then you start coming back up again. What happens to all that kinetic then? Right, starts turning back into potential. Now, in the real world, where most roller coasters exist, the second hill is never as tall as the first. Why? Right. Okay. The roller coaster would never make it up a hill that was the same height as the first. Because in the real world, there is drag, air resistance, friction against the rails, all of that kind of stuff. That's why roller coasters are so loud. Right? The sound is not just the screaming of the people on board. Okay? It's the rubbing of all those metal parts together. That is evidence that energy is being lost. Okay, well, not lost. It's being converted into forms that are no longer doing useful work. All right? Will sound help propel the roller coaster back up? No, it will not. Okay? It is just flying away from that system. All right? So it's not doing anything useful anymore. All right. So, looking at this here, I would like for you to answer these questions right here. All right? They have to do with these diagrams and with these graphs. Okay? Can I make it a little bigger? Yep, if you don't have that sheet. Better? Yes, I would like you to do... Actually, you don't have to do number 3. We've talked about number 3 enough. You don't need to write what the law of conservation of energy is again. Okay? All right, I'll give you a few minutes on that, and then we'll go over them together. Okay. So if you notice that number 4 is messed up, good. If you didn't notice 4 is messed up, you will in a minute. What is that graph saying right there, that potential energy versus height graph? This is height, right? Along this axis here, this is height. So height increases as you move to the right. Agreed? That's how a graph is supposed to work, right? Then what's wrong with this graph? It's saying that at some height, potential energy magically starts to decrease. That shouldn't happen, should it? Potential energy should continue to increase as height increases. Yes, that's exactly what should happen. All right, what they didn't do here is this should have actually been potential energy as a function of time. So that as the ball was in flight and went higher and higher and higher, it got more and more potential energy, but then it reached its maximum height and then began to come back down to Earth. This axis, if we want that shape, should be time. Okay? If we want potential energy versus height, that's our graph. Okay? It should look like that. Agreed? It should make sense. Now, B, same problem. Okay? They've got kinetic energy as a function of height. And yes, the first part of the graph is right. But then for some reason, magically, as height increases, kinetic energy just suddenly gets bigger. Last time I checked, things don't just magically start accelerating upwards at some height. All right? It doesn't work that way. All right? This graph should look like this. If we want to have a graph with this shape, it's kinetic energy versus time, not kinetic energy versus height. Okay? That is why your axis should have numbers on it. Agreed? These axes do not have numbers on them, and that is why they are messed up. Okay? We could make this a function of height if we made this the maximum height. Okay? And either one of these, 0. Then it could work. I don't know why anyone would make a graph that looked that way, okay? But you could make it work that way if you labeled your axis and actually put stuff on it. You could, but I don't know how you would manipulate the energy. Yeah. Okay. All right. So number 2, pretty straightforward. Okay. So when we got the types of energy that the football has, when it leaves the kicker's foot, mostly what? Mostly kinetic. I mean, it might be a little tiny bit off the ground, but for the most part, it's kinetic. Okay. What does it have at a point halfway up? Right. Kinetic and potential, or you could say, what answer could you put for every single one of these and have it be right? Mechanical. Yeah, you could put mechanical energy for every single one of those and it would be right. Okay. For C, what types of energy does the football have at the highest point in its path? And kinetic. Because it's moving forward. If you threw it straight up in the air, then it would only have potential. Because it wouldn't be moving forwards. But because you're kicking it horizontally, it's a true projectile. Okay? And as a result, it's actually still moving at some speed forwards as well. So it would have both. But again, that's why mechanical energy would fit here and be the correct answer in any situation. All right? Where's the total mechanical energy the greatest? Everywhere. Because mechanical energy stays the same. Once the kicker has kicked the ball and done the work on it, the ball can never have more or less mechanical energy. It can have more or less kinetic, but as kinetic goes up, potential will go down and vice versa. Right? But the mechanical energy will never change. That's the really important thing to realize about that particular question. All right. Everyone good with that? Okay. Now, for these ones here, okay, I do have the answers on there, but just so that you can check how you're doing as you go along, you also have these on yours. All right, so I would like you to do question number 5. Okay, it's pretty straightforward. It looks like a lot of work, but it's not. Okay, 6 and I think I cut off 7, so you're definitely not doing 7. Okay, yeah, so let's do 5 and 6 for now, and then we'll look at 10 and 11 after. You guys have 7? I just cut it off? And you have 8 as well. 8 I'm not so worried about because that's the pendulum. We already talked about it. Oh, a ball thrown vertically. Oh, no. Okay, yeah, let's do 5, 6, and 7. 5, 6, and 7, guys. All right, so you're going to have a quiz, work energy theorem, last one, tomorrow. Okay, I'll tweet it later on today. These are not for homework. Right, we'll start tomorrow by going over questions 5 and 6. I don't think you probably had too much trouble with them, but we'll go over them. Okay, and then right after that, I'm going to set you up with exactly the type of conservation of energy question you will get on both your unit and final exam. And we'll go over how to solve it, okay, so that you have a good solved example. And then we'll probably go through a few more. Work on that. Wednesday, lab. Okay, Thursday, efficiency. Friday, review. Monday, test. Okay, it's all coming up.